also falling under Michelle's program, the Advanced Ore Body Knowledge Program. And Stratafy is a startup that started 2019. We came about trying to develop, and we successfully did get to the point where we self-funded enterprise level GIS software back end that would have the capability to democratize complicated data sets within a typically siloed environment where specialists with specialized software could effectively share data. But part of that process was to develop the next phase, and that was a plugin that could start to visualize data underground and specifically looking at the rock face. There was a moment that we realized that we can start to affect safety and risk and start to look at that in a different way by trying to democratize the generation of 3D models, getting a 3D model of the rock face at the point of safe declaration every day, getting that model out quickly, cost effectively, and with wide adoption within the industry. So I'm going to maybe jump over all of this, just talk a bit about the team. This is us, where we developed a scanner. Essentially, the scanner in a big picture story would be a magic wand. At the end of this magic wand, there's a scanner, there's a see-in-the-dark device, let's call it a handheld device, and then a software environment or an ecosystem where all of the data could be processed and beneficiated and then distributed within the mining organization. So I guess a bit of what I'm going to talk about is a bit of a testimonial of the process that we followed with the Mandela Mining Precinct, how we got this really great idea to get momentum and to get it deployed and tested and to become a reality. So we started with the first part in the last year, so 2023. That is just developing the scanner portion. That's at the end of this telescopic pole. And this is a really great way to remove the miner with that moment of safe declaration from the actual unsupported hanging ball. And you get your miner to extend a scanner into that space and do a scan and a rapid 3D modeling that whole space while still standing underneath the supported section. So advancement would be maybe 2 to 3 meters, and that's the only region we want to scan, right? So having a fairly affordable, robust piece of kit that's going to have a one-button operation and then giving near real-time feedback, that's the vision here, right? So the second part of that would be a handheld device, and the third part is integrating into the open back-end or the open source spatial data ecosystem. There's a bit of the tech umbrella where we thought about this in a different way. How are we going to move from LiDAR, which I love, it's one of my favorite technologies, but we realized it's not going to work for us in a scenario where it's going to have to be a piece of kit that needs to be robust, cost-effective, really simple to operate with, maybe semi-skilled workers, even not being specialists and not needing to recalibrate the device in the particular environment where we're going to work. So that was a big push for us. We took inspiration from Syntopic and synoptic cameras from the Cold War era, rethinking the way that a camera could be used, or a set of cameras could be used rather, and also realizing that the limitations with photogrammetry in a GPS-denied environment, and also the lighting conditions within the stopes and the tunnel development areas is so challenging for photogrammetry. We needed to solve for that. So a lot of the work we did was around rethinking existing technologies and processes and software applications. So we made sure to look at designing a scanner that's going to touch on all of those limitations. There are blue boxes. They are talking about there's a handheld device, and then there's a process that we have a resident rock engineer in our team that's got a proven process, and we're going to have to make sure we fall into that proven process that is practically executable. It will help us to get to market on mass. Mass adoption is going to be key here if we really want to do there's one magic thing, and that is build a 3D model of every panel or every working space every 24 hours. So this rapid sprawling of the 3D model is what we're after here with mass adoption. And then obviously the programmatory software bits that is already embedded in our Stratafy online platform. So I'm going to skip around through all of this. I suppose many of these photographs and shadows just to impress you, to show how much we did achieve over the last year. This was test article 1. We had to just validate some of the angular calculations we made early on to have multiple cameras in on one rig. Some of these are supposed to be gifts that should their own. There we go. All right. So you can see the approach here would be to have a scan with multiple cameras, onboard light sources, multispectral lights, accelerometers, and other gadgets to help us to build a 3D model real quick. We came back from that first test phase. This was some calculations we did for test article 2. It was designed, really elaborate system with 8 cameras and lots of energy needs, and it was a hungry baby. Kept us awake at night. But we pushed through, and right then above you can see some of the multispectral light sources. So we've got near infrared as well. So everything is built custom and in-house. We don't buy off-the-shelf electronic hardware. We've got an electronic engineer who's got a team that helps him to get electronics designed, built, and locally soldered and assembled and tested. So this is kind of showing you, just keep this in mind, this is showing you the rapid prototyping, fail fast and fail hard type approach. We know it's not very academic, but we need to test multiple things at once, like the housing, the lighting, camera arrays, and some of the firmware and software that we employ to do things. So we want to maybe fail on 2 or 3 different things when we really push the equipment to its limits. So we test to failure, right, every time. So these are some thermals we got from hardware and software. These are early power supplies. We had Wi-Fi connectivity to control this unit, because ultimately this has to be a one-button intelligent tool. Your worker or your semi-skilled laborer or the miner needs to switch it on and switch it off. This device needs to know where it is, what it's doing, distance from region of interest, frame rates, speed at which it's moving around, and all of these parameters needs to be automated. So these are just some of the cameras. We went to assembly of the test article, tested at the Wits mock mine. This was a great day for us just to validate a lot of the controls, and there you can see some of the scanning methodologies we had with our early, let's call it a hammerhead, right? This broomstick with eyes. It worked really well. We had a 0 shadow array, which is super important for programmatory purposes. The shadows you see on the 3D model here is induced. We added it just so that you could actually visually see the rock structures or the geological structures with the photographs, RGB photographs overlaid. But in essence, this is a 0 shadow model where we needed to build or reproduce the details with high fidelity, and thus removing the shadow was important. So the next steps would become evident later, why we need to then add shadows back in. Anyway, so after going underground, so this was the underground visit with the test article 2, and we failed hard there with some of the firmware. A lot of late nights, a lot of hard work. This was a visit that really made us rethink everything from firmware to hardware, and also the amount of cameras. So we started redesigning after this. We did some validation. Many things were great. If you look at the 0 shadows around the mesh, normal lighting would render shadows behind the mesh or behind wires or in deviated surfaces like that. So that was a great test of the lighting. Some lessons we learned was that we need to reduce power consumption and complexity. size. We need to reduce the processing. It was just taking too long to process. And this handheld portion, the scanning portion of our project, does a lot of filtering and pre-processing, and that we needed to simplify. We got down to 4 cameras. Electronic engineer loves us. The software guy loves us. This was designed in record time too. You shall know we didn't sleep too much. Again, everything from scratch redesigned, power supplies, and that was the resulting test article 3. So test article 3 is very close to prototype. We are now going to change some more things. What's evident if you look at the image there, that we are testing multiple refractory layers or refraction with lights shooting through double medium, because eventually we need to be able to build a model that is going to be an intrinsically safe housing. Inevitably, that's going to have to have some kind of a covering of all of the apertures and lenses, right? So that was quite important to test for that. So those are the next tests coming up. This is the actual, let's see if the GIF is going there. These are some of the actual tests we did underground again. Test article 3. So I think it's clear to see that we believe to go underground and test this in a real world environment. We wanted to make sure that works theoretically will also work in practice. For instance, traveling down the cage all the way to the workplace. How mobile is this? Working in the stope, working with this as a user, experience this from firsthand from a user point of view. All of those things was important to us, because remember, we got mass adoption in mind. It needs to be affordable and executable, this whole plan. So that is kind of the way it'll be used. This was the early versions of test article 3. And so resulting point clouds came out. We could overlay some important detail, including low-hanging features in a hanging wall. We could do some discontinuity set extractions. So we could look at something that be really helpful for the miner in the stope visually, but also for rock engineers and the specialists within the mining fraternity or within the organization or on site, as these models would start to become available within a few hours after the miner has inspected this with his handheld device, right? So there's this moment where you can rotate and look at these models on your handheld device, and you could really inspect whether some of these features are connected, because your lamp might only cast a 1 meter diameter light source, and something might be connected across the panel, and you won't notice that because you move the light around. So having great light, having a model that's really well lit and intuitive to interact with was the idea here. So that's all part of where we are developing towards. And then why not LiDAR? Why did we go for photogrammetry? I think it's important just again to think of the design principles and the way we're going to get our route to markets the most successful we can. And it was all about getting a passive sensor that is robust, it's not fragile. You don't need to do constant calibration on it, and making sure that it is cost effective. If you truly want to make sure there's one throughout the mine, this could be part of your safe declaration moment. Every section will have their panels scanned and modeled daily. We can start then to add additional features that will make financial sense to the mine and to the production team and to geology and survey. So distance from peg, distance from ventilation, or collecting data about heat and humidity over time, measuring methane at the face. So looking at all of these additional sensors and additional data points that you bring back within the shift, almost moving your rock engineer to the first moment in the shift, rather than trailing 2 days behind with the models and completing the rock mass index, for instance. So all of these things were important to us, but not just from the point of view of physically identifying immediately dangerous features within the newly blasted area, but also to add value to the rest of the downstream activities that happens within the mine. So that's about the song and dance. I hope I made it in time. Thank you very much, Augusta. Thank you, Ned.